here's what you're going to write at the top of the page. You're going to write the phrase discontinuity. Discontinuity. And I'm going to try and explain what discontinuity means. Have y'all seen those in movies? Spider-Man. Right? Yeah. Where the person's hair is messed up in a certain way, and then they go to the next person that they're talking to, and then they come back and their hair is still messed up, but it's messed up in a different way. All right, so if you can think of that idea in film, if you can think of that idea in movies, you can understand what a discontinuity is in a function. In a function, a discontinuity is a break, some kind of break in the function. Now, you are already familiar with two kinds of discontinuities. A hole is one kind of discontinuity. In fact, we're going to write this down. Excuse me. There are three kinds of discontinuity. All right. In fact, that right now on this video, if you're watching this video from home or wherever else, you've probably seen discontinuities all over this video. All right. Three kinds of well, let's just say three kinds. One of them you're familiar with. One of them is called a hole, okay? And does anyone remember how to identify a hole in a... First of all, what kind of function does it have to be most of the time? It has to be a rational function. Most of the time it has to be a rational function. The other possibility is that it has to be a piecewise function. Now, we briefly discussed holes the other day. In rational or in piecewise functions. So a hole is usually an irrational function, and it's what typically happens when you have a hole.
They don't connect.
Right, but why? How did you find a hole just given, not given the graph, but just given the function? Do you remember? Yeah, you had factors, right? And you could have something that you could cross out, something you could cancel out. Okay, so here's the thing. So like if we had, x plus 5 times x minus 4 over x minus 3 times x plus 5, right? We have something we can cross out here. And therefore, this indicates a hole at x equals negative 5. Because negative 5 is what you would plug in to get 0. If I plug in negative 5 here, what will this equal?
0.
And what is 0 times this?
0.
0. And if I plug in negative 5 here?
0.
And 0 times this is?
0.
So we would end up with 0 over 0. So here's the rule. Almost every time, this is an indicator, so I can't make sweeping statements in math because there are all these exceptions. But generally speaking, anytime you see 0 over 0 at a point for an x value, there will be a hole for that x value. So this function has a hole at x equals negative 5. Because when you plug negative 5 in, you get 0 over 0. Is that okay? It really is that straightforward. Here's the problem, is that you will forget to look for the hole. Did y'all hear that? Yes. You'll forget to look for the hole. One of the things we're going to do today is we're going to look at some piecewise functions, and the piecewise functions are going to have more than one hole, and you have to know that you have to look for both kinds of holes. Okay, so that one kind of discontinuity is a hole, usually when you have a rational function, and usually when you get 0 over 0. All right, that's the first kind of... Now, here's the interesting thing about a hole, though. Watch this. If I have a graph here, and if I have at an x value, if I have a hole at an x value, this is hugely important. I cannot possibly overemphasize, even if I spent the entire class period talking about it, I cannot possibly overemphasize this concept. Even though there is a hole at x equals negative 3 here, what is interesting about what the graph is doing from the left side and from the right side? What's interesting about that point? Okay, let me ask you this. Could we make the function continuous? Yeah, we could, right? We could make the function continuous by filling the hole. If we fill the hole, then the function becomes continuous, right? And because of that, holes are called, write this down, they're called removable discontinuities. And that's pretty much the only kind of removable discontinuity. So it's important to understand the difference between a non-removable and a removable discontinuity. And because you can fill a hole. So if I filled the hole, then would there be an output value? Then would the function be continuous? Yeah, it would. Okay. Now, the other two kinds of discontinuities that we're going to talk about, they are not removable discontinuities. All right. By the way, another way of thinking about continuity of functions is a function is continuous if you can draw the graph of it without picking up your pencil. Okay, does that make sense?
Yes.
Okay, so like if the graph looks like this, am I picking up the marker? I never picked it up from beginning to end, right? It's continuous, isn't it? Yeah. So in order to draw a function with a discontinuity, here's what you would have to do. You would have to draw a portion of the function, then pick up your pencil, then draw the rest of it. Do you see that? I had to pick up my pencil in order to draw the rest of the graph. So there's a discontinuity. All right. Are you guys ready to move on to the second kind of discontinuity? All right. Any questions about holes? Okay. Now, well, let's get to that other subject later. So the second kind of discontinuity is, well, actually, I'm going to call that the third one. But thank you. Yes, a jump is a kind of discontinuity. But I want to focus on the ones that you guys know already. The second kind is called an infinite discontinuity. An infinite discontinuity. And infinite discontinuities are the same things as vertical asymptotes. You guys remember vertical asymptotes? Right? They're easy too, right? An infinite discontinuity is basically a vertical asymptote. Okay? So watch this. What if I have x plus 5 times x minus 4, like I had before, over x minus 3 times x plus 5, right? We've already said that this function has a hole. I got to put a y equals here. We've already said that this function has a hole at x plus 5, right? So we could cross out the x plus 5 and it would still be the same function, only we couldn't plug 5 in. Or negative, excuse me, we couldn't plug in negative 5. But what else do we know about this rational function?
There's a vertical asymptote at x equals 3.
That's correct. There's a vertical asymptote at x equals 3. Because x minus 3 can't be crossed out, but it would still cause the denominator to equal 0. If I were to plug a 3 in, I would get 3 minus 3 is 0, and I would get 3 minus 4 is negative 1. So I would have a here, write this down, you guys know what that means, right? This equal sign with a slash through it means not equal to, right? Not 0 over 0. If I have not 0 over 0, that's a vertical asymptote. Not 0 over 0 indicates a vertical asymptote. Well, watch what this graph is going to do now. It's probably, this also has a horizontal asymptote at 1. I don't know if you noticed that right off the back, but this particular function has a horizontal asymptote at, but don't worry about that right now. I just want to be a little accurate with my drawing. So, and I'm pretty sure that this graph on the left does this. Pretty sure. And on the right, it does this. I think. Let's see here. And there's a hole here. Okay? So now look. Look at this graph. Did I have to pick up my pencil to then go over here and draw this part of the graph? Yeah. Now here's a good question. Can I remove this discontinuity and make it continuous? Nope. Because even if, you may say, well, Mr. Ryan, what if it did this instead? What if it did that instead? Now maybe you could remove the asymptote and make it continuous. Nope. Yeah, that's correct. It's still going up forever from both directions. So this infinite discontinuities or vertical asymptotes are not, they're not removable. All right? Are we okay right now with infinite discontinuities? Okay. All right. So last kind, Prashant, what's the third kind of discontinuity?
Jump.
A jump discontinuity, that's right. A jump discontinuity, you had a tiny bit of experience with it the other day when one of the problems that you did had a jump discontinuity. I believe it was question number 2, where the graph did something like this. Does this look kind of familiar? It did something like this, right? Okay. And what happened was, up until a certain value, was it 3 or 2? 2, okay. All right. So up until, well, let's do 3 on this one. So here, up until 3, the graph has a value of -1, but starting at 3, and I got to make one of them a hole. See, look, because they can't overlap. I can't have a closed hole on both of them. It can't be defined in 2 places. What happens if this graph is defined in 2 different values for the same x value? No, what if they're both included? Then it is not a, we're going all the way back probably to 7th grade. You guys had to learn about the definition of a function, and one of the first things you learned is called the vertical line test, right? The vertical line test, right? It's not a function. If it fails the vertical line test, it is not a function, right? Yeah, so you go along and you're like, oh, it only hits at one place, it only hits at one place, it only hits at one place. As long as it only hits at one place for every vertical line, it's a function, right? But if this is filled for about at x equals 3, if at x equals 3, the relation is equal to both -1 and +1, it is not a function because it fails the vertical line test. Excuse me, that's not a vertical line. It fails the vertical line test at 3. Does that make sense? If that made sense to one person in this room, I'm happy. All right, made sense to Octavia. Guys, check it out. If a graph approaches one value from the left side, but a completely different value on the right side, that's automatically a jump discontinuity, okay? And I'm going to give you a really classic example of a jump discontinuity. This one, what I'm about to write on the board, messes with young people learning math all the world over. I want to talk about this function right here, okay? Y is equal to the absolute value of x over x. Now, here, please hear this. All right. It can be helpful to learn math sometimes. It's called, okay, there's 4 main ways to understand math. You can understand math verbally, which means through conversation, right? Through conversation and description. You can understand math analytically. That's where you turn everything into a function and you explain things using equal signs and variables and addition and subtraction symbols, right? That's analytical. You can understand math graphically. How am I explaining discontinuities to you right now? I'm showing it on a graph, right? Okay? Right. And some people understand things better graphically than they understand them analytically, but it's important to understand it both ways if you can. The 4th way that you can understand math, and this is where some of you hopefully will have an epiphany. Another way that you can understand math is called understanding math numerically. If you're the kind of person that when you sit down at a test or you sit down to do homework, a way that you try to understand what you're doing is you start plugging in numbers to see what happens, that's called a numerical understanding of math. Okay? I do it. I understand things numerically a lot. And here's what I'm saying is, in order to understand this, you could understand this graphically. We could graph it, but it'd be... Here's the funny thing about graphing this. In order to graph this, you would probably have to do it numerically first if you don't immediately understand it, okay? So what I want to do is I want to try and understand this numerically, okay? And here's how you understand something numerically, is you choose arbitrary values to plug in. I usually start with whole numbers, and then to get a really good understanding, I start wondering what would happen if I put in decimal values. And then I put in negative values. You know what I mean? So, Shade, pick a number to plug in. 5. All right. If I put a 5 in here, now if I put a 5 here, where else do I have to put a 5? At the bottom. And what is the absolute value of 5? And what's 5? And what's 5 divided by 5? 1. So we know that if we plug in, now we're going to do it graphically. 1, 2, 3, 4, 5. If we plug in 5, we know the answer is going to be 1. Right? All right. Tiara, pick a number.
Can it be a big number?
It should be between negative 10 and 10 because that's all I have on here. 9. All right, we're going to plug 9 in. Tiara, what's the absolute value of 9?
You said what?
What's the absolute value of 9? 9, right? Okay, so then what is 9 divided by 9? 1. So we know that if we were to plug 6, 7, 8, 9 in, we would get 1, correct? All right. Brashan?
-2.
-2. Brashan wants to plug in -2. All right. What's the absolute value of -2? 2. And what's 2 divided by -2? Think about it one more time. What is 2 divided by -1, right? So at -2, the answer is -1, correct? All right. Does anybody find that a little bit interesting?
I get it.
You see what's happening?
So it's going to be 1 or -1?
That's correct. The answer is either going to be 1 or -1. Under what circumstances? When will it always be 1? Positive number. When will it always be -1? Right. So now, why don't we think about numbers closer to, when do numbers go from being negative to positive? At 0. Can we plug 0 in? No, because if we plug in 0, we'll get, right, you would think it was a whole because it's 0 over 0, but it's not going to be. Yeah, watch what happens. So let's pick, here's what you can do. If you can't plug 0 in, what you can do numerically is pick a number really close to 0. Yeah, 0.75, or how about 0.1 or 0.01? All right? What if we put in 0.01? What's the absolute value of 0.01? All right, and what's 0.01 divided by 0.01? 1. It's 1, right? Okay, so at 0.01, the answer is 1. So presumably, what's going to happen here? It's going to have a value, a constant value of 1 all the way up until what? We know that we can't plug in 0. It's a whole. So I'm going to put an open circle. Does that make sense? Okay. All right. All right, so now let's put something in that is negative but really close to 0. Negative 0.01. What is the absolute value of negative 0.01? 0.01. And what is 0.01 divided by negative 0.01? -1. So we know that all these negative values are going to equal -1. So it's going to be a constant value of -1 except up to 0 where it is not defined. And this is the graph of y equals the absolute value of x over x. Yes?
So you can have two holes in the same x.
See, that's the thing, is they're not holes. Remember, with a hole can be filled in and made continuous. An open circle doesn't always mean a hole. You can have an open circle at the end of a piece. What kind of discontinuity is this, Taylor? That's a jump discontinuity, right? So in most cases, the reason I'm doing this example is I'm trying to show you that most of the time, a jump discontinuity is going to occur with a piecewise function. You're going to have a Frankenstein function, and you're going to look for a jump discontinuity. You see a Frankenstein function, f of x is equal to these three pieces, all different intervals, right? And your first thought should be, one of your first thoughts should be, is there a jump discontinuity anywhere? Because you could very easily have a jump discontinuity, which we're going to do today in 30 minutes. Within 30 minutes. Or I'm going to show you how to easily, like in 2 seconds, to find a jump discontinuity. All right. Now, except, guys, hear this. Except the other kind of function that could give you a jump discontinuity without being a piecewise function is a function that includes what?
0.
Good thinking.
1.
What's in this function? Absolute value. Because absolute value functions, in a way, are actually piecewise functions.
Wait, what? Let's go back.
Absolute value functions are fundamentally piecewise functions. Let me show you an example. Okay, have you ever seen the, can I erase this one? Does anyone? Well, it'll be in the video. All right. Has anybody, look at that, I got rid of my lines. Has anybody ever seen the graph of y equals the absolute value of x?
Yes.
Okay. Do you recall that it looks like a V?
Yes.
This is the absolute value of x.
Yes.
It looks like a V. Because if I plug in -3, the answer is +3. If I plug in -1, the answer is +1. If I plug in +1, the answer is +1. And if I plug in +5, the answer is +5. Are we okay with this? This is it's a form of linear function, but really, how many linear functions is it? It's actually 2 linear functions, right? It's y equals -x. In fact, here's what we're going to say. That this function is equal to -1x plus 0, which is -x. But only when x takes on a value that is less than 0. Now, I want you, do you guys, compared to all the other piecewise functions we've been doing, how is this different right here?
It doesn't have an in-between.
Yeah, this is not between. It's going, where's it going all the way back to? No, it's starting at 0 and going backwards to -infinity. That's right. Yep. And then this other piece is a linear function. It has a slope of 1 and a y-intercept of 0. So that's 1x plus 0 or just x. When what? When x is greater than 0, right? Now, it is defined at 0. So we need to pick one of these two to get the or equal to. It doesn't matter. Meaning we have to, because you can plug 0 into this. And so what you're looking at here, this is the same thing as this, only as a piecewise function. Does this have a jump discontinuity? No, it doesn't. So let's say that we have f of x is equal to, write this function as I write it, x squared minus 10 when x is between -4 and -1. 7x minus 4 when x runs from -1 up until 5. And then -x plus 4 when x runs, oh, excuse me. Oh, I looked at the wrong one. Hang on. What am I looking at here? 7x minus 4. Oh, sorry. 2x squared minus 19. Sorry about that. I was looking at the wrong one. All right. Sorry about that. 2x squared minus 19. When x runs from 5 up to 7. All right. First, the first thing you want to look for, guys, if you want to make steps on a piece of paper, put a 1 with a 0. Here's your first step. Whenever you see a piecewise function, the first thing that you probably want to do is you want to check the continuity of your x values. Is there a break? Starting here and going up to here, is there a break? There's not, right? We're going from -4 up to -1 inclusive. Then we're picking back up at -1, going up to 5. 5 is not included here, so we want to see if it's included down here. Sure enough, 5 is included and goes up to 7. So we do not have a discontinuity in our x values. If there was a discontinuity in our x values, that would be the first. There is at least a hole if there's a discontinuity in x values. See, we're already using the word discontinuity, aren't we? Right? Yeah. Okay. Now, step 2. All right. Y'all ready for this? This is a longer step, but in your mind, once you're good at it, it takes you like maybe 30 seconds to do. Here's what you're going to do. For every transition value, do you guys remember what a transition value is? It's a value that shows up on 2 consecutive lines of a piecewise function, right? Okay, so -4 is not a transitional value, right? -1 is a transitional value and 5 is a transitional value, right? Here's what you're going to do. For every transitional value, say that again. Plug it in. I want you as my lawyer. Plug it in to both pieces that it touches. So we're going to plug -1 in here, and we're going to plug -1 in here. If we get the same number, no, think about it. If it's the same number, it's continuous, right? If we get a different number, then not a hole. It's a jump. That's correct. Yep. Yeah. All right. All right. So now watch. We're going to plug -1 in. Okay. What's -1 squared? 1. And what's 1 minus 10? -9. So what I'll do is I'll usually like kind of jot down a number there and next to it. Now we're going to plug -1 in here. What's 7 times -1? -7 minus 4? Same number or different number? Therefore, we have a jump discontinuity at x equals -1. Next, plug in 5. If I put a 5 in here, what's 5 times 7? 35. And what's 35 minus 4? 31. Now let's plug 5 down here. What's 5 squared? And what's 25 times 2? And what's 50 minus 19? 31. So what's happening at 5? Is it continuous or is there a jump? It's continuous.
Okay, so you plug in
The transition value, yep. That's a phrase I made up, so it's not official math or anything. Transition value, that's what I call it. Yeah.
Okay. So you plug in every transition into every point it hits, and if it's the same as continuous, if it's different,
It's a jump. That's correct.
okay.
Does that make sense?
That's what happened with number 2.
Yeah. That's exactly what happened because you plugged it into one side and it was -1. You plugged it into the other side and it was +1, right? And so we had a jump discontinuity. Are we good so far? All right, I'm going to put another one up here and I'm going to have you. I'm going to give you all a few minutes and I want you to see if there are any jump discontinuities up until 3, okay? All right, so step 1. Now I'm going to let y'all do this on your own, but I want to do the first step with you. Are the x values continuous?
Yes.
All right. So we got -3 up to -2, inclusive of -2, up to 1, inclusive of 1, up to 2, inclusive of 2, and up to 3. All right, so if the x values are continuous, then we can be sure at first that there are no holes, right? All right, take about maybe 2 minutes or 3 minutes and see if there are any jump discontinuities. All right, so how many transition values are there? How many? Transition values. 3. We got -2 is one of them. 1 is a second one. And then the third one is 2, right? That's a weird color. Must have mixed with black somewhere along the line.
Yeah,
All right.
it's so white, like smart attributes, so it's blending in with the
Oh, that makes sense. Yeah. I should still be able to pull it off. All right. Hey, guys, can you guys settle down a little bit? All right, so look. We're going to plug this -2 in. When we plug in the -2 to the third power is -8. -8 plus 5 or 15 is 7, right? But here, it doesn't matter what we plug in. The answer is always 10, right? So 7, 10, they don't meet up, not the same number. Jump discontinuity. All right, plug a 1 in. It doesn't matter what we plug in. The answer is always 10, right? Plug a 1 in here. So we'll put a 10 here. So plug a 1 in here. 9 times 1 is 9. 9 minus 4 is 5. So jump discontinuity. Lastly, plug a 2 in. 9 times 2 is 18. 18 minus 4 is 14. And then plug 2 in here. 7 times 2 is 14. And therefore, since we have the same number, it is not a jump discontinuity. It is continuous. That's correct. How are we doing? Are we good? Yes. Do you guys like this easy subject? I hope, maybe? Okay. All right, let's do another one. Now we're gonna, well, what I'm doing now is, I'm now gonna move you into the realm of identifying all 3 kinds of discontinuities in a single piecewise function. And I think we have enough time to do it. We do about 5 minutes for each one. So let's say that we have x plus 3 when x goes from 0 up to 4. Then 7 when x goes from 4 up to 6. And then when x goes from 6 up to 10, we have 2x minus 5. Right. Go ahead. All right. So Brashan says there's already 2 holes. How do we know that for sure?
There's no equal to or 4.
Yeah, we do not have continuity of our x values. Okay, here 4 is not included and here 4 is not included. Here 6 is not included and here 6 is not included. Therefore, this function is automatically not defined for 4 and 6. So if somebody were to say, well, what is f of 4? You would have to say, well, that's undefined. Okay? Because there's nowhere to plug 4 in. Now, occasionally, watch this. I want you to see this. Occasionally, what they might do with a piecewise function is this. Look at that. Now it's defined for all values of x, right? Look, here, 4 is not included, right? Here, 6 is not included. So sometimes what they'll do on a piecewise function is, when they're not included in these values, they will then come down here and include them one piece at a time, one little, for each individual x value. Now they have closed the holes. Right? But now if there are now it could be a jump discontinuity. That's correct. Okay? All right. Okay, so let me get rid of this. I'm going to go back to what it was, because this is what I meant to do. This is what I meant to do as the lesson. All right, now, so how many transition values do we have?
2.
Yeah, we got 4, and what else? Yeah, even though they're not defined, they're still transition values. And they're still the numbers that we plug in. So if we put a 4 in here, what do we get? 7, right? And then plug this in, 7. So no jump. But what is there? A hole. So there is a hole at x equals 4, right? What if I did this? What if I did this? What did I just do? I filled in the hole. I just filled in the hole. You know, there's another way to fill in the hole. Watch this. Boop.
Oh my God.
All right. If I just put an or equal to on here, that fills in the hole too. I could put an or equal to up here and fill in the hole. Okay? Are we doing okay? Yeah. All right. Go ahead, Shade.
Does it matter which number that you put in front for to fill in the hole? Because you put x equals 4, but then you put like 14 in front of it. What if it was like 6, but it was still x equals 4?
Oh, so if I put a 16 here and then x equals 4, this does not fill the hole. It still has a hole. All right. Because this is what this is going to look like. See, at 7 up to 4, right? 1, 2, 3, 4, 5, 6, 7, right? And can we make this 8? Is that okay? All right. So we've got this linear function that goes up here that does this. And then we have a constant function that stops here, right? Is this okay, Shade? This is I just graphed those two. X plus 3. Guys, you got to settle down. X plus 3 and 7. Right? With a hole here. Now, I just defined for x equals 4, I defined it at 8. And even though it is defined at 8, it still didn't go where the hole is. It went to the x value, but it still didn't fill the hole. There's still a hole in this part of the function. All we're saying is that the function is now defined at 4, but it's still a hole. A better way, instead of calling it a hole, it would be better to say we have a removable discontinuity. And the way we can remove the discontinuity is by redefining the function at 4 as 7, which would now fill the hole and remove the discontinuity. I know I'm pushing the limits of what y'all know about math, and that is good. Right? That's how we learn. Okay, now, last one here. Let's get rid of this. How about here? How about at 6? If I plug 6 in here, what do I get?
You get
7, right? So again, let's see, 1, 2, 3, 4, 5, 6, 7. We have a hole here, and we have but it is a hole, and we have a slope of 2 on this, right? So this, what I'm drawing here, this is actually the graph. This is actually the graph of that function, right? It goes up to 10, so it goes a little higher, way up here, right? And it closes off. So there's the graph of this function. And it has 2 holes in it. Are we still alive?
Yeah.
Yes.
We're okay? All right, let's do the next one. We have 2 more to do. And you will have learned a lot of good stuff today if you learn all these things. Write this example down. It's x plus 3 times x minus 2 over x plus 3 times x plus 1. Okay? When x runs from -4 up to 0. Okay? Next piece, 3x minus 2 when x runs from 0 up to 4, positive 4. All right, last piece, x plus 1 when x runs from 4 up to 7. First thoughts, what?
There's a hole at 0.
Yeah, 0 is not included. This function is not defined at 0, right? So we may have a hole. It's either a hole or it's a, I heard it,
Jump.
or it's a jump, right? It's only a hole if both functions meet at the same place at 0. If they meet, jumps supersede holes. If it is both a hole and it is a jump, then it is a jump discontinuity.
Oh, so you're saying like
Yeah.
the jump overrides the hole?
Yes, that's correct. Yep, a jump overrides a hole. Okay? All right, so now, because you jump over a hole. I'm full of them. Okay, so, all right, so look. Now, let's now do what we're accustomed to doing, and let's look for a jump discontinuity. How many transition values do we have? 2, right? We have 0 and we have 4, right? So if we plug 0 in here, what's 0 plus 3? 3. And what's 0 minus 2? And what's -2 times 3? Okay, so -6 over. Now let's put 0 in here. What's 0 plus 3? And what? Sorry. That's okay. I see. Yeah, but except that it's not addition, right? Except it's not addition, it's multiplication. Yeah, so this will be 3, right? Because 0 plus 1 is... So what's -6 divided by 3? -2, right? All right, so this is -2 when you plug in 0. What if I plug in 0 here? It's negative 2, right? So there is a hole at x equals 0. We could say, hole, watch this, hole at x equals 0. All right? Now, let's go to the next transition value. Let's plug 4 in. What's 3 times 4?
12.
Minus 2? 10. Yep. All right? Now let's plug 4 in here. What's 4 plus 1? 5. So what do we have going on at 4? We have a jump at x equals 4. I can already see the multiple choice question forming. You know, at x equals 3, this function has a jump, B, whole, C, infinite.
Okay.
D, no discontinuity or continuous.
Okay. Whole. Well, let me write this down.
Yep, whole.
Whole? Okay, define what a whole is.
A whole is when the function would be continuous, except it's not defined at that point. Well, it's not defined. No, that's not a good way to say it either. Let me explain. There is a calculus way. Watch the video. The end of the video. There is a calculus way to define a whole. And I can't give that to you right now because we're not in a calculus class.
Okay, so can you give me the...
Okay, yeah, the idea is a whole is a removable discontinuity. The way you identify a whole is either a break in a piecewise function or the way you already know how to find a whole. Yeah, go ahead.
You just cancel out the x plus 3.
Yeah. All right, so guys, listen, just because I'm videoing and just because I didn't give you a quiz today doesn't mean that y'all shouldn't work hard to understand this stuff, okay? All right, so look, and I don't think you're not working hard, it's just that you're distracting me. All right, so look, watch this. Brashan says that we can cancel out x plus 3 in this piece, right? So what would we plug in here? That indicates a whole, right? And what would we plug in to get a whole? Negative 3. Now, listen, this is important. Just because there is a hole at negative 3 doesn't mean that this function has a hole in negative 3, because in order for this to indicate a hole at negative 3, this function has to be defined with negative 3.
Go back.
Okay. If negative 3 would never be plugged into this piece, then there's no hole.
Oh, I get it.
See, is negative 3 on this interval?
Oh, yeah.
Look. Yeah, it's in between, right? Therefore, there is a hole at negative 3.
So you're saying...
So you're saying if it wasn't included...
Right, if it wasn't included in that, if this said from negative 2 up to 0, then there wouldn't be a hole at negative 3. See? What's that? Well, you could draw it if you were drawing it. But a lot of times you don't work with these graphically, you work with them analytically.
Okay.
Okay, so now what else though? Look here. Vertical asymptote at,
X equals negative 1.
is that on this interval? Yes, therefore we have an infinite discontinuity at x equals negative 1. And I didn't write, here, see where we wrote hole at x equals 0? I can put a comma and say x equals negative 3. So this thing is full of discontinuities, right?
It's just all discombobulated.
Now, do you see this function right here? See this linear function? Linear functions don't have discontinuities. So we don't have to check it. See how we just checked this rational function? We don't have to check this piece because linear functions don't have discontinuities. And this is another linear function. In fact, all polynomial functions do not have discontinuities. Yeah, so like x to the third power function does not have a discontinuity. The only way it's going to have a discontinuity is if it is a part of a... No. Yeah, what are we looking at overall here? If it's a part of a piecewise function. Okay? Last one. We got one left to do. Last one. So this is all of them. There's a vertical asymptote, there's a hole here, and then there's a hole at 0 because it's not defined, but the two functions meet up at the transition value, and then at this transition value, it's different, so there's a jump.
Okay, so the hole is when
Yes, that's correct. By filling the hole, it would then be continuous. It would then be continuous.
Okay.
Yeah.
And then, what's the other one? Jump.
A jump is when you have a completely different value from the left side and the right side.
Jump is completely different.
Yeah. See, on this side it's 10, but on this side it's 5.
Okay, so it's completely different. Okay.
Yeah.
And what was the other one?
Infinite, that's a vertical asymptote, which you already know how to identify. It's when the denominator equals 0, but it doesn't get crossed out. Shide.
Okay, so you see how you have that 0 and then there's no equal sign?
Yes.
You didn't have to plug that in because it's not.
Well, we did plug it in because we wanted to find out whether it was a jump or a hole.
Okay, so you still have to.
So we still plugged it in, and we got -2 on one side and -2 on the other side. Because it's the same number, it's a hole, not a jump. Okay? All right. Let's do one more. We have just enough time for one more, but this one I can't ask you any questions. I just have to work through it. All right, so this last one is going to be, we're going to have x minus 5 times x minus 8 over x minus 4 times x minus 5 when x is between -7 and 0. And then x plus 3 when x is between 0 and 2. And then it's x minus 3 times x plus 13 over x plus 1 times x minus 3 when x is between 2 and 3. Okay, so now look at this. Continuous, not continuous at 2, no or equal to. Therefore, I could potentially have a hole at 2. If it's not a hole, then it would be a jump discontinuity, unless there was an infinite discontinuity, because infinite discontinuities, they rule over all of them. All right?
So it's like a step ladder.
Yeah, huh? Yep. Infinity is higher than the jump over the hole. Okay, so now look. So now I'm going to plug the transition values in. If I put a 0 in, I get -5 times -8, which is 40. -4 times -5 is 20, right? And 40 divided by 20 is 2. If I plug in 0 here, I get a 3. Because those numbers don't match up, it's a jump discontinuity. So I have a jump at x equals 0, right? Now I'm going to plug 2 in. Plug 2 in here, 2 plus 3, that's 5, right? Plug 2 in here, and I get 2 minus 3 is -1. 2 plus 13 is 15. 15 times -1 is -15. Over 2 plus 1 is 3. 2 minus 3 is -1. -1 times 3 is -3. And -15 divided by -3 is +5, right? So it does meet up, but because 2 is not included, it's a hole at x equals 2. Right? So we got a jump at 0. We have a hole at 2. Now, all right, watch. Guys, please see this. This is about one of the most important things that you can see. I know that I can cross out x minus 5, indicating a potential hole at 5. Except that 5 is not on this interval. Therefore, no hole at 5. At least not because of this. There would be a vertical asymptote at 4, except that 4 is not on this interval. Therefore, no vertical asymptote, right? Moving down here, this is a linear function. Linear functions don't have discontinuities, right? Moving down here, we've got an x minus 3 and an x minus 3, right? Meaning that there's a hole at 3. Except that 3 is not included, therefore there is no hole at 3. Right? Lastly, this indicates a vertical asymptote at -1. Except -1 is not on this interval, therefore no vertical asymptote at -1. Okay? So do you see how you have to identify the quality that indicates there's a discontinuity, but then you have to check to see if it, yeah. It don't, well, it does. It has a jump at 0 and it has a hole at 2, and that's it.
Okay.
Yep.
But as far as like with the holes and stuff like that, it doesn't have any holes.
It doesn't have any additional holes. It doesn't have any holes or infinite discontinuities because of rational functions. All right?